Hi everyone, last parametric video then. And realized in the previous video, in the previous example, we found the normal to this curve at t equals 1. But let's just recap and actually answer part B, which said convert it into Cartesian form, which remember we'll only do if the question asks us to do it. We don't need to do it otherwise. Because remember, if we're trying to find the normal or the tangent, if x equals 1 over t plus 1 and y equals 1 over t minus 2, we would do our dy by dx equals and then use the chain rule. Hopefully I've picked a good example of where the curve's going to be horrible. We did see that curve in the previous video. I think it looked like that one. So we've used the chain rule. We don't need to convert this into Cartesian form. But sometimes we're going to be asked to do that, and the way to do that is if it is not, so if you see a mixture of cos same angle, sine same angle, make cos and sine the subject, and then use that cos squared theta plus sine squared theta is one trick. Or it could be like sec and tan, you know they go well together, cosec and cot, all Pythagorean identities will work. If it's not trig though, you need to make t the subject in both and then equate them. So, for example, to make t the subject here, I'm going to have to times up by t plus 1, aren't I? And then divide by x, because I'm trying to eliminate t. So therefore, well, let's do this for a sec. Maybe you'll like this one. So that's t plus 1 is that. Just bear with me here. What about for this y? How about if I times by the t take 2 and then divide by the y? Can you see that if I add 3 to both sides, why has he done that? Well, because that way I get t plus 1 is 1 over y plus 3. But aha, t plus 1 also equals 1 over x. So therefore 1 over x is 1 over y plus 3. And I've made it into Cartesian form. Do you see? Made it into Cartesian form. And the objective is not to get y equals, because getting y equals might be really horrible. Is it really horrible? Let's have a look. So if I make 1 over y equal 1 over x take 3, and then if we make the denominator the same on the right hand side, so 1 minus 3x over x, and therefore y must equal x over 1 minus 3x. So actually the graph's probably not that bad, because that is going to be a kind of 1 over x looking graph, a reciprocal graph, which it kind of does look like in that one, but there's going to be constraints in terms of our x and y's for this to work, so we won't go into that level of detail at the moment. But that was a nice little trick, wasn't it? Spotting t plus 1, spotting t plus 1, but in general you probably won't spot tricks like that. So we can go back from where we were there. So t plus 1 is 1 over x. Make t the subject. For the y, we started from here, didn't we? So t take 2 was 1 over y, so therefore t is 1 over y plus 2. And therefore you can make that equal that, which is the same thing. Okay? This video is meant to be about parametric integration, but I just want to, again, just further reinforce what's going on here. So this time we've got a curve, and remember a curve in parametric form is described by x and y, isn't it? So x equals and y equals together form one curve. So that there is a curve. What does that look like in autograph? Let's have a quick look, shall we? Go on, it's only Friday, end of the day. It's nice to have a look at a nice curve. Yeah, I do make myself laugh. T cubed minus 2t. Okay, so whoa, looks like that. Awesome. Awesome curve. Like that. And then we've got this line. The line y minus x equals 1 crosses that curve at a, b, and c. So I could put that in. Y minus 1 equals 1. So that's there. So we can see it crosses here, here, and it's going to cross somewhere up here. Okay, the question says find the exact coordinates of a, b, and c. Now, putting this thing into Cartesian form is going to be an absolute nightmare, and that's going to be your challenge question when you get into college next for this. Now, it's a complete waste of time making that thing Cartesian form. What you need to understand is that when these two things intersect, this and this curve intersect, x and y are the same, aren't they? They're the same. In all intersections, they're the same. So y minus x equals 1. That x is the same as that x, and that y is the same as that y. So can you see you can literally sub it in. So y is t cubed take 2t. X is minus t squared minus t is 1. So now we have t cubed minus t squared minus 2t take t, so that's minus 3t, minus 1 is 0. How would we find out a factor to that? Well, we could use our C2 factor theorem perhaps, or we could use our numerical methods, but I reckon the factor theorem would work. So if I let f of t be t cubed take t squared 3t minus 1, I just need to find that factor. What could it be, do we think? Could it be f of 2? So answer cube. So this is what you do, isn't it? If you remember from C2, you just make up ones. No, f2 don't work, you get minus 3. Minus 2. Answer cube 2 squared. 1. You get minus 7. Nope. Minus 1. Answer cubed minus answer squared minus 3 answer minus 1. Yay! So f of minus 1, success, gives me a bit of C1 revision for you here, C2 revision, sorry, gives me 0. And therefore, by the factor theorem, x plus 1, not x though, because we're doing t's, t plus 1 must be a factor of f of t. And now we can use our division, might as well use our new long division method, right? So what do I need to times t by to get t cubed? T squared, don't I? Multiply that out. T cubed plus t squared. T cubed all sorted. Got t squared. But I need minus t. I need minus t squared, don't I? So I need to times this by minus 2t. So that's minus 2t squared minus 2t. Bang, bang, sorted. Got minus 2t, but I need minus 3t. So I need to subtract another t. So minus 1. Minus t minus 1, and we're all happy. And now we can factorize this one. So t plus 1, what's that? T, is this going to factorize? No, don't think so. So, ugh. Now we've got to factorize this thing then. So t squared minus 2t, going to have to use the quadratic formula, or my magic calculator. So just going to use my magic calculator then. So t is minus 1. And what we get is t is minus 1. T is 1 plus root 2. T equals 1 minus root 2. I didn't actually have my magic calculator, I thought I did. So I just paused the video and did it through the quadratic formula. The old classic. And now we can find the coordinates, the exact coordinates of A, B, and C. So since t equals minus 1, I know what x is. because x, remember, was t squared plus t, and y was t cubed minus 2t, but does that make, yeah, that's fine. Okay, so therefore I can plug that into there. So when t is minus 1, x is going to be minus 1 squared, so that's 1, minus 1, so that's 0. When t is minus 1, t cubed, that's minus 1, minus 2, so that's 1. So there's your first one, 0, 1, and you get the rest of the idea. You whack those in. Let's actually get on to what the video's intention. The intention of the video. Parametric integration. So, consider the parametric equations x equals t squared and y equals this thing. This describes this curve here, which looks a lot like a quadratic, doesn't it? Find the area of the region R, and we're going to need to derive the integral formula for this, because, again, we will not convert into Cartesian form unless the question asks us to do that. So, for part A, to find any area, you can see on here, this is between x and y, when x is going between 0 and 9. It's exactly the same start. To find an area, you would integrate y, wouldn't you, with respect to x, between x is 0 and x is 9. But we're working in parametric form. And you know from substitution that we could rewrite this as dx by dt times dt, because they effectively, in inverted commas, cancel, don't they? Do you see? All you need to do, so the dt by dt effectively cancels. All you need to do then to make something parametric is to write your normal y dx and then dt dt. It's that simple. You'll be amazed how many people write y dt and then dx dt. It doesn't make any sense. You start from the original, don't you? And then you can add that dt by dt on, so it cancels, so nothing's changed. You see, you're still integrating y. So this is our parametric area formula. And so now we can just fill in the gaps, but obviously we're not using x is 0 and x is 9 as limits anymore. We're using t. And so x equals 0 into there makes t equals 0, doesn't it? Because t squared equals 0, so there you go. X equals 9 into there gives t squared is 9, so therefore t equals plus or minus 3, but it doesn't matter. Just always take the positive one when you're square rooting. It doesn't matter if I took minus 3, I'll get the same answer, basically. But we're going to take t equals 3. Okay, so always take the positive one when you're square rooting your limits. And now we can just fill this in. So r equals ry is 2t times 3 minus t. Cool. And dx by dt, we're just literally filling in that section now. That's 2t, isn't it? dt between t is 0 and t is 3. We're going to have to multiply that out. So t is 0, t equals 3. So 2t times 2t, that's 4t squared, times by 3 take t. Again, we're going to have to multiply that out. So that becomes, whoops. So 4t squared times that is 12t squared subtract 4t cubed dt equals limits 3, 0, plus 1 to the power divided by a new power, so 4t cubed subtract t to the 4. And then just literally going to shove those limits in. So, and you could use the same aim system as we normally use. So if we put that in, so 3 first, 4 times 3 cubed minus 3 to the power of 4. Do that again. 4 answer cubed minus answer to the 4. So that's 27. Subtract 0, so the answer is 27. Yeah, because the last limit is 0. Finally then, I know it's not very neat. I'm not very good at neat. B says find the volume generated when you rotate by 2 pi radians about the x-axis. We know what the volume equation is from class, don't we? The volume equation is pi y squared dx. Why is that? Because remember, each integration splits up an area into an infinite number of lines. If you rotate a line round an axis, you get a circle. And as you go along the axis, that's what dx means, adding up all those infinite number of circles, you get your shape of the curve spun round. So it's going to look like that, isn't it? Almost like a kind of football, American football. Sorry, rugby, sorry. Anyway, and the area of a circle is pi r squared, isn't it? And r, your radius, is your y value. Do you see? That's where that formula comes from. Again, to make it parametric, because here's your limits, 0, 9. To make it parametric, it's exactly the same. dx by dt, because the dt's cancel and you're left with what you had before. And again, we need to convert our limits, so t is 0 and t is 3. And now we would just integrate this thing as normal. So pi, what's y squared? So that's 4t squared, 3 minus t all squared, times by dx by dt. We found that out earlier was 2t dt. So that's pi. I think you're getting the idea of this. So that's 8t to the 3. That times that. And then we'd have to expand those brackets out. So 9 minus 6t plus t squared dt. And therefore we get pi 8t cubed times 9, 72t cubed. But to be honest, I wouldn't do that. I would take the 8 out, so it's just nice and neat. So pi, so 9t cubed minus 6t to the 4 plus t to the 5 dt. And then obviously just integrate as normal. I don't think you need me to show that. You can finish that off if you want to. That's it. Parametric integration.